topic, of course, we have been developing solar and wind onshore, but these options are now slowly diminishing, and its time has come to think offshore. We may have some projects soon, or may not, but with the government inspiration to increase the renewable energy to 70% by 2030, we need to tap these options as well. So the content of my presentation will be mainly, I'll spend a lot of time on offshore wind. That's my expertise really. And we'll talk about the offshore development overview, offshore connection options, and development of an offshore hubs. Then I will move on to floating PV, and as Tushar mentioned, briefly touch upon the wave or the marine structures, and finally summarize. Moving on to offshore wind. Now, one main advantage of going offshore is there are no buildings or structures to interfere with the free wind, so there are less turbulences. The wind resource is much better than on land, and you can always find large sites, less resistance for planning permission. Of course, the fish who will be affected will not make any the court cases against these wind farms, so that's an advantage. The fewer physical limits on size and weight. Of course, there are disadvantages such as the installation and maintenance is very complicated compared to onshore sites. The cost can be 10x more than the onshore option, so fairly high cost, and not only the cost for the wind farm, also the capital cost for the transmission options will increase due to the sea involvement. Having said that, the offshore capacity has been increasing exponentially. As of 2020, the total world offshore wind energy wind capacity stand at 32.5 gigawatt, and UK is having the highest share. You can see some of the sites in the world, and as you can see, the UK has the 42% of the total offshore wind capacity, and all these the dots of light green color indicates site already in operation, and the size of the circle shows the size of the wind farm, and the light yellow color shows the partially online systems, and the kind of dark yellow shows the sites under constructions. And you can see that the Germany is having 31%, Netherlands having 10%, and you can very clearly see that most of the offshore wind farms are concentrated in the Europe. Maybe this is only the European sites. There may be sites in the rest of the world. And one interesting thing is this is the distance to shore to the water depth. And if you look at this, you can very clearly see that early wind farms, offshore projects, were concentrated on 2020 envelope, which is 20 water depth at 20 kilometer distance from the show. However, today you can see that some of the already operating offshore wind farms are 100 kilometers away from the seashore and at a water depth of 40 meters. So these are now moving away from the seashore. For example, the Dogger Bank, which is coming in, I'll show you later on a diagram, coming in north of the UK, is having 170 kilometers from the seashore, and the size is nearly 13 gigawatt. Okay, let's look at wind turbines. This is the evolution of wind turbines. If you look at the early wind farms, they utilize fixed speed induction generator. FSIG stands for fixed speed induction generator. They are the same machines that are used in mini hydros. Basically, what you have is a induction motor running as a generator. If you want, we have few FSIG systems. One of our classic old machine, which was installed at Mirijaville in Hambantota, is a 600 kilowatt FSIG machine. But around 2000, the onshore machines move on to what we call DFIG, which is the doubly fed induction generator. It's again an induction generator. Only difference is this induction generator is a squirrel cage. This one is a wound rotor, which is having some power electronics to manipulate the speed of the turbine. However, more recently, all the onshore wind turbines became fully power converter geared or gearless. These are using permanent magnet machines with back-to-back converters. So you basically decouple the AC system with the mechanical or the wind farm side. Somewhere around 2005, we start seeing wind turbines of a diameter 100 meters. We were having a capacity of 3.5 megawatt. What we have in Mana is very close to this one, which was installed more or less this year. Then, of course, we start seeing more bigger ones. For example, most of the new wind farms are direct drive permanent magnet. Here, what you are seeing here is not a the gear wheel or something. These are all lateral magnets what you see there. And then one American company is introducing high temperature superconducting direct drive machines, but other than some pilots, there are no commercial scale machines available. But today, especially to cater for the offshore market, all the wind turbine producers has come up with huge wind turbines. This is a 15 megawatt each turbine having a rotor diameter of 240 meters. They are gearless or geared full power converter. Now, just to get an idea about the largest wind turbine with the size of the largest the Airbus, this is Airbus A380, which is the largest aeroplane available today. And you can see when you put that in together with your wind turbine, you can just get an idea about the size of a wind turbine. Of course, there is one German design, Aerodyne Hvdc, which has two rotor constructions, but there is a huge difference between this one and all the commercial available other wind turbines. All these wind turbines are 3-bladed, whereas this one is 2-bladed. That is because of the 2 turbines. So it's more like 4 bladed. And you can also see the floating structure. I'll come back to them in a minute in more details. Now, when the foundation is a key, now usually how you do, you use a monopile and you drive the monopile into the seabed, and on top of the sea, you will see the transition. On top of that, you will see the work pressure. And this is the monopile is driven to ground, to the seabed using a large ship. There are specialized ships for wind farm constructions, and you need to hire one of those to drive these monopiles into the seabed. And this is how it looks after it's been erected. And this is the last piece of the monopile. And on top of this, you will get the wind turbine tower. And you can see that the wind turbine tower is installed on that top of that section. And once the wind turbine tower is installed, then you need to install the wind turbine, and this is the nacelle with you normally put the nacelles first and the blades later. And you can see that this is, even though this is ship, it can lift. Remember, as I told you, the height of the entire structure may be around more than 150 meters. So your ship need to go all the way to, that it has the cranes mounted on the ship, so it will go to the level of half of the, or at least to this yellow piece, and from there you use the cranes to lift the nacelle, and then you sometimes install the blades before or after. You can see here they have installed 2 blades, and 1 blade is waiting to be installed. One it is go up. However, as my topic suggests, today the wind farm foundation is not fixed structures like this. Here, as you can see, the monopile is driven all the way, and the new ones, you will see the monopile is basically floating. The spar buoy is one such design. Here you make sure that the center of gravity is below the center of buoyance. And how do you do that? You use some weights on these mooring lines. We call it ballasted plane. And the structure was originally demonstrated in Japan in 2013 for 2 megawatt, and you will see it shown later on in one of my slides. There are already commercially operating wind farms using this kind of floating structure. So in order to keep of course, the spar buoy will be in vertical position, but in order to restrict any lateral movement and any the tilting and so on, you have these mooring lines. They are anchored to the seabed. This is the second floating structure, which is called submersible. Here you can see that there are few columns, usually trapezoidal kind of an arrangement, and the column provides the kind of a stability, hydraulic stability, and you have a pontoon to keep it floating. And in order to keep the foundation again in the position, you will use the mooring lines, and there are drag anchors at the bottom of the seabed. Originally demonstrated in Portugal in 2011. Then another demonstration was there in Japan in 2013 and 2015. But these are for single machines. But today you will see more and more of these applications. The other one is tension leg platform, where there you can see that the steel wire is directly vertically connecting the floating structure to the seabed. And this is of course demonstrated in Germany in 2016. Here you can see that the Europe is again leading, because obviously they are having a lot of wind farms. And as of 2020, there were a total of 62 megawatt of wind fleet at European sites. And they are expecting there are around 7 gigawatt of floating wind available in the Europe. And these are the sites available today. You can see that some of them are already commissioned, some are under construction, but they are using all different kind of floating types, semi-submersive, barge. This is the TLP's tension leg platform, and spar buoy, and so on. And they are not very big wind farms, but number of turbines are limited. But of course, as it picks up, you will start seeing more and more in the future. Now, there's one thing you need to consider, the control of wind generators. Now, in modern wind generators, we have two controls. Usually, the wind turbines will not rotate or will not generate any electricity below a certain wind speed. We call it cutting wind speed. And this particular wind turbine, the cutting wind speed is 3.5 meters per second. And once it passes the cutting wind speed, the wind turbine generator will produce electricity. And sorry, I just lost my electricity, and I was told by CB they are changing the in-feed to Kiribati Komura, so hopefully I should get electricity back. But you may not see me, I will be in dark. And hope that CB promised that they will only use a couple of minutes to do the changeover. And as I told, from 3.5 meters per second, okay, the CB kept their promise, the electricity is back. At around 3.5 meters per second, wind turbine blades will start rotating. Below that, of course, you break them, because no point of generating any electricity. The electricity generated is less than the losses inside the turbine, so no point of rotating the blades, so you break them. At 3.5 meters per second, you release the blades, and they are rotating and produce power. And as some of you may know, the power output is proportional to cube of the wind speed. It's given by a equation half Cp rho A u to the cube. And at 12 meters per second, we call it the rated wind speed for this particular wind turbine. The power output of the wind turbine reaches the rated power. And if you let the wind turbine to rotate as it is, the power output will increase. It will follow the same cubic pattern, but that will destroy the generator. So in order to make sure that your generator is operating at its rated value, 2 megawatt, you use what we call the pitch control. The whole idea of pitch control is you usually use the pitch angle at around -2 degrees to extract the maximum power from wind. But as the wind speed goes about 12 meters per second rated wind speed, you slowly rotate the blades using a pitch actuator, and you can rotate up to 90 degrees. By doing that, you spill the available wind power. And by doing that, you can maintain the power output at a constant. Now, in normal wind turbines, of course, this is pitch control will not have any other consequences. But in floating wind structures, as you can see on your right-hand side figure, there are some forces and movements at the floating structure. And as you could see on y direction, there is a rotation called the foundation pitch, and that pitch has a connection or the dynamics with the pitch controller. So you cannot simply do the pitch control as you do it in an online platform. You need to have some coordinated control to minimize the floating structure flipping and to maintain the power at its rated. So there are clever controllers already been introduced, and at around 25 meters per second, we call the cut out wind speed. You break the blade again and let the wind farm to stay still until the wind speed comes back to its operating region. So this is typical operating structure of a wind turbine. Please interrupt me anytime, or you can wait until the end. I don't know how the organizers wanted to have the questions. I don't mind either way. Talking about the transmission options. Now the how you transmit the power from wind farm to the onshore to be consumed by the people depends on how far your wind farm is from the seashore. Now here I am showing three options. If the wind farm is smaller, like less than 100 megawatt, and if the distance to seashore is smaller, less than 30 kilometer, you will use medium voltage AC, like 33 kV AC to connect the wind farm to the seashore, to the main grid. If the wind farm is of the size of 90 to 500 megawatt, having a distance around 90 kilometer or less, you will use high voltage AC or around 220 kV or 400 kV and connect it to a AC substation. If the wind farm is very large, like 100 megawatt, 200 to 100 megawatt, having a distance from the seashore about, like if it is 1,000 megawatt, 40 kilometer, if it is a 200 megawatt, 300 kilometer, you need definitely to use DC connection. You cannot use AC connection. Main problem with AC connection is, as you could remember, the AC also have active power and reactive power. And these long lines will have reactive power, and they take the most of the capacity of the cable and leaving very little capacity to transmit the wind power to the onshore. Therefore, when you go with DC, there's nothing called reactive power. It's all active power. So you can transfer large amount of active power to the main grid. So these are the transmission options available in the market today. And this is a typical AC connection. What you are seeing here is this is a typical connection. You have wind turbines as erected offshore. Then there are, the array cables like this one. This is the array cables. Then you have offshore substation. Now, this is another key component on an offshore wind farm. I'll come back to that in a minute. Then you have cables, these kind of cables. If it is a submarine cable, you use some floaters to mark them. And then you have the land cables. And finally, it is connected to an onshore substation. So these are the components of a AC connection. And as I told you, the offshore substation is built onshore, then shipped to the site on a particular day. Now, this is the 90 megawatt Barrow offshore wind farm in the UK, and they ship the offshore substation on 12th August 2005 using a ship having a large crane, not the ship, the large ship. Now, what I was told by my friends who were working at Alstom, now building this platform is very simple, easy, because this is a GIS substation, and the main turbine power producer like Siemens, Alstom, or ABB, they have enough know-how to do that. But there are only few ships that remember, these are the weight-wise, these could be like 300 tons or something, very heavy. So there are only few ships available to carry these substation to the offshore the foundation. And remember, again, this offshore foundation, there are now floating offshore foundations with this, they have the launching pad here. So you need to take the substation there and keep it there. Now the issue is getting these ships. You need to book the ships, as I was told, at least 6 to 8 months before the date that you are going to move the platform to the site. But the problem is, you have to, because the number of ships are limited, they are asking the full amount to pay. And if on the day of loading the substation, if the sea is very rough and you cannot move the ship, you will lose all the money. So I was told by my friends that all the mathematical models that people are talking about, you need a supercomputer to model the sea conditions, predict the sea conditions 6 or 8 months ahead, and then pay whatever the amount for the ship, because you need to make sure that you make sure you book the ship, as well as you make sure that you hit the deadlines. Remember, if you can't hit the deadline, then what happens is there will be large fines imposed by the grid operator, and the what amount of money they are going to lose, they are also huge. This is a typical cable. Usually you can use XLP cable, but there are mineral insulated cable as well. And you can see that large cables like 400 kV having a cable cross-sectional area of 2,500 millimeter square. You cannot have 3 cables like that. It is a single cable. Can take a continuous load of 650 to 890 megavolt ampere. So you will need so many cables to take whatever, depending on the size of your wind farm, you need to select the right voltage and the right cable. This is a typical guideline. This is, in fact, I borrowed from one of my friends' slides for his principal design engineer, somebody at Siemens. And you can see that as the distance to shore increases and as the megawatt capacity increases, of course, you have to go with DC, but around some points you can live with AC, 220 kV. Then you can, below certain distance and power levels, you can use 132 kV. And for very short distance, low power applications, you can use 33 kV. This is a typical HVDC connection, and you can see that this is the wind turbine generators. They are connected to a AC bus, and then use AC to DC converter, and you transmit DC, and on the other end, which is at the onshore, you convert DC back to AC and connect it to the grid. And as you can see, there is always the break-even point. Now here I'm comparing break-even point of a 132 kV AC with 500 megawatt DC transmission, and the initially you will have large cost for DC, and that is because the blue one is the DC one. You will have large cost for the DC. However, as the number of cables required to DC transmission is less than number of cables required for AC transmission, the gradient will become less, and it will cross the AC line at certain distance. So you can see that in order to transmit 1 gigawatt of power, you will need 3 core 132 kV AC cables, 5 of them. If you are using plus or minus 300 kV HVDC system, you only need 1 core 2 cables. So that will drastically reduce the cost as the distance increases. There are 2 technologies used for HVDC. One is the current source inverter technology, which use a device called thyristor, and other one is the voltage source converter based HVDC, which use a device called IGBT, insulated gate bipolar transistor. Now here in the current source one, the DC side current is constant. On the voltage source converter, DC side constant. This is kind of the comparison. I'm going to skip that. Basically, okay, very quickly. Now, one of the main advantage of line commutator or the current source converter is less losses compared to the voltage. But in terms of the size, the world largest HVDC scheme right now operating in China. Somebody is mic. Can you make sure that whoever, I really can't, there are so many people, so I don't want to find who is, but can you make sure that you mute your mics, otherwise it's disturbing others. And the largest current source converter, thyristor based one, which is in operation, is using a DC voltage of plus or minus 800 kilovolt, and it is transmitting 6,400 megawatt of power. So which is huge, whereas the voltage source converters are not that big. They can only transmit 400 MVA at a DC voltage of plus or minus 400 kV. And you can also see that the HVDC, original HVDC was based on what we call the mercury arc rectifier, move on to thyristors later on. They were in service since 1954. The current source converters only came to service in 1997. Sorry, voltage source converters. Now, the main problem is each device can only handle around 5 kV. So in order to get 400 kV, you will need quite a lot of devices connected in series. So this is a string converter, and usually now they use the roof mounted structures. So this is mount in the roof, and here you will find so many thyristor or IGBT switches to obtain the voltage level required. Now there are two competitors originally came for voltage source converters. One is the normal converter produced by ABB, but the other one is what we call the multi-level converter produced by Siemens. But now everybody is producing the Siemens approach. Very quickly, the Siemens approach use many levels to produce your AC voltage. So it is, if I draw how it produce the AC voltage, each of these switch will produce a level. The next switch will produce another level. Next switch will produce another level. And that this is the way you get your sine shape. So you, by manipulating the turn on period of these switches, you can get a nice sine wave. Usually you have around 200 of odd number of switches here to get many steps as required. Right, I will see whether this will work. I'm going to change the speaker. This is a small video which shows how these converters are operating. If you can't hear the sound, you will at least see the way they are operating.
2 and 3 level topologies generate rectangular waveforms of
So this is the ABB original design, which is a PWM converter. That's basically. Again. That's basically show you the latest way that the wind farm power is transmitted to the main grid using DC grids. Going further with DC grid, this is actually the design they are planning for Dogger Bank. Now, each of these square represent a 1 gigawatt wind farm array. You can have simple radial connection to the grid. You can have one larger cable with two, the cables, or you can have an integrated approach like this one. Here you can see that in the first one, each 1 gigawatt is connected to the main grid using single cable. There are the two 1 gigawatts were connected together and use offshore platform and then connect one single cable. Here also you have offshore platform, but which is a smaller offshore platform. Here you have two cables and integrated. So this will give you more redundancy. So you can increase number of, the 1 gigawatt blocks and how they connect together. Remember, the Dogger Bank will have 13 of these blocks, and there are so many options to connect them together. And UK is also planning not the UK, the Europe is also planning what we call the European supergrid. The whole idea is the south of Europe will have a lot of solar farms, roughly 30 gigawatt of solar power. And the north of Europe has a lot of wind power, which is 50 gigawatt of wind power. So if you can connect them together, you will get best diversity. And with that energy mix, you should be able to run the Europe, as a sustainable system. But of course, this may, I don't know what will happen with UK leaving the Europe, but you can see that most of the offshore sites are at the UK. So these offshore sites will be the one node of these hubs, and they may come, may not come. And this is the Dogger Bank. As I told you, it has approximate generative capacity of 13 gigawatt. So you will have a lot of blocks connected, as I showed you, and it has this national grid has been trying various connection options to the seashore. And as I told you, that the shortest distance from the seashore to the Dogger Bank is 170 kilometers, and from there you will see Norway, a few hundreds kilometers away. So there are the designs going on, but this is not yet started construction. And in Dogger Bank, they were considering, in fact, we were doing some studies for Dogger Bank. Here, I'm showing you two different ways each 1 gigawatt block can be connected. Here, the connection of the two blocks as well as connection of the other blocks are on AC side. Here, in the second one, you can see that the connections are on AC side, but connection of the adjacent blocks are using DC side. So you use DC here, you use AC there, and of course there are all kind of the design considerations for connection of Dogger Bank. Okay, I think I have spent nearly 45 minutes talking about floating solar, floating wind, including some basics of wind. And of course, I'm not going to spend much time on these two topics. I can't remember the time available. Somebody remind me how long I have for my presentation, please. Tushara, can you remember? Hello? Okay, let me go back and find it out. I hope that people can hear me. I didn't really,
Yes, sir.
Yes, sir. So how long I have for my presentation, please? Okay, let me go here and try to exaggerate this. Okay, okay, so I have another, nearly 30 minutes, so that's fine. I'm still doing okay with the time. Okay, so can you see the slides, please?
Yes.
Yes.
Okay, thank you.
Yes.
So moving on to floating PV, again, Sri Lanka has already, I have seen that SC has already called for expression of interest to do feasibility study of floating PV plants in Sri Lanka. They are mainly, of course, you don't put floating PV on sea. You mainly use lakes, reservoirs, and so on. But again, you can see that there is a increase in cumulative installed capacity of floating PV. Today it stands around 2087 megawatt electrical. And every year you can see that nearly 600 megawatt electrical is connected to the systems all over the world. If you look at the distribution, there are many less than 2 megawatt, but most of them are more than 15 megawatt. And China is leading with floating schemes. Nearly 73% of floating schemes are in China, which counts for more than 300 projects. Japan is next, then Korea, then Taiwan. So you can see that when it comes to the offshore wind, the Europe is leading. When it comes to floating PV, Asia is leading. This is a typical structure. You have a pontoon. On top of the pontoon, you put all the PV modules. Then there is a combined box, and you may have another central inverter again on the floating structure. And these are the mooring lines connected, anchored at the bottom of the seabed. And then you have the submarine connection to the shore, and then you connect it to the nearest grid. Talking about the solar modules, there are, we mainly talk about the silicon, but there are so many solar modules produced by different manufacturers in university level, research level, and so on. And what we normally see is what we call the crystalline silicon. Poly and monocrystalline silicon is the main market. Maybe 80% of the market is captured by silicon. Then we do have gallium arsenide. We are having a very efficient multi-junction solar PV. I will show you in a minute. There are commercial thin film solar arrays. We have amorphous silicon, cadmium telluride. I do have now cadmium telluride on a roof. Cadmium, indium, gallium sulfate or something. This is the quantum dot. No, this is not quantum. This is, I can't remember. So there are so many commercial thin film technologies available. Then emerging thin films are perovskite, which is Russian material. We have organic, we have dye-synthesized, and we have quantum dot. Now, these wafer-based are the famous ones, but you will find certain thin films one also using for certain applications. As I told you, the multi-junction PV cells produce the best efficiency. Now, remember the silicon is only affecting from nearly from 200 nanometer wavelength to 1100 nanometer wavelength of the solar spectrum. This is the solar spectrum. It cannot go into the high energy parts. So the silicon solar cells will only capture certain components. Now, the idea of the multi-junction, you use 3 different materials, gallium indium phosphate, gallium arsenide, and germanium, to capture a larger portion of the solar spectrum. But how do you do that? You use prisms to break the sunlight into these 3 wavelength components and send them to the right material, which produce more protons and more electricity. And NERL is upgrading this site every other week. And you can see that the multi-junction has reached an efficiency nearly 48%. These are the best laboratory efficiencies. Don't misunderstood. These are not commercially available at that rate. And if you look at the silicon, the blue ones are the crystalline silicon, mono, and you can see that the silicon is having an efficiency in around 20. But look at this one. the one with yellow, red circle with filled with yellow. That is that bit. Now this perovskite, which is a new material found somewhere in 2015, they are working with Oxford University and reached the efficiency is closer to silicon within few years. Remember, for silicon to come there, it took few decades. Now these cells are available commercially, but there is a huge problem of their stability, especially when they are exposed to certain weather conditions. They will not work properly. So this is the issue I was told that these companies are trying to resolve right now. And you look at the cost. The cost has been coming down. This is the residential level and this is the utility level. At utility level, as everybody knows that cost of solar PV has come down to $1 per kilowatt hour, which is a very, kilowatt peak electricity, which is a very small amount, and it is comparable to many conventional power. And what this graph shows is various components. You can see that the module has the largest pie. Then the inverter, the soft cost, again, fairly high. And then you have the hardware and so on. And now the solar connection also, what you do is the solar produce DC. You use a DC-DC convert mainly for MPPT, maximum power point tracking. Then you use a single phase inverter to convert DC into AC. Then use filters and grid interface and connect it to the grid. Of course, the controller will have MPPT, PWM, reactive power control, voltage control, and so on. There are various connections used. This is a central inverter. Mainly for floating structures, you use a central inverter like this. All the arrays are connected to a single inverter. Or you can use sub-array inverters. As here, few arrays are connected to separate inverters and they are then connected in parallel. Or you can have string inverters, again connected them in parallel. Now, floating platforms used for solar PV. This is the pontoon, and these are coming in a modular structure, so you can, vary the size of this pontoon as you wish, depending on the site requirement. And there is a special mounting structure to mount the solar panels at an angle, tilt angle, as you require. Now, typically you use around less than 15 degree tilt, depending on where your the solar panels are mounted. This is the raft system, which is used by two companies, Solar and Takiron. They have more like a floating raft, not a structure. If I show you the next slide, here you can see that there is a floating raft for the solar panels, and then the bridges which can connect them together to form the array. Then the Norwegians are introducing what they call the membrane system. Basically this membrane, on top of the membrane, you put all the solar panels and the inverters and so on, and they are being demonstrated in some places in Norway. I will again run a small video for you to get an idea. Let me see. Now, did you hear the what you call the audio of the video that I played before? Can somebody confirm?
Yes, we could hear.
Okay, so I will change the same thing. I will try to change it to the system. So I hope that you will hear this one also. So you can see that it's easy for them to mount the solar system because everything is mounted on the membrane. And you can see that the older waves, sea waves, can be taken by the membrane. So you will, having a stiff structure, you will need a lot of mounting. But here you will have, only the membrane, which is a large typhoon, which can be mounted, and then you put all the solar panels on top of that. Right. So these are the anchoring types used for floating solar. You have the bottom anchoring, you can have bank anchoring, or you can have pile anchoring. Right. This is the topic that I'm not at all have any expertise. The floating solar, of course, I was involved in a project in Bangladesh in Lake Mahamaya. It's called Lake Mahamaya, which where one of the main difficulties we were having was the depth of the lake, the variation of the depth from what you call the dry season to wet season is quite remarkable. So the designing of mountain structures was tough. In fact, I was not working on that part. I was working with a British company mainly on the electrical side. But I don't have any experience with marine energy. I'm sure there are experts maybe listening to me. You have tidal range. The tidal range is one you find in France, where you have a barrier and use low head turbines to generate electricity. I do have some good connection to tidal range, which is the tidal barrage that is planned in Cardiff, but which was never, the design team never could persuade the government to fund it because it was not easy. It was 9 gigawatt, so huge tidal barrage. But of course, it was not economical, so never materialized. So now the Cardiff team is kind of given up the tidal barrage and thinking of what they call the tidal islands. Then, of course, the tidal stream, which is very similar to wind turbines, only difference is the turbines are inside the sea, using the sea waves to generate electricity. Then, of course, we have many different wave energy structures. But one main difference between the other floating structures that I described and this one, this is still at its the beginning. They compare to many gigawatts of solar and many gigawatts of wind. Here what we have is less than half a gigawatt, around half a gigawatt. And out of that, the main portion is taken up by the tidal current. Most of the installed capacity is tidal range, which is 522, and the remaining part is tidal current around 10 megawatt, wave around 2 to 3 megawatt, and I don't know what OTC stand for. So different. So you can see that the tidal range are the main marine energy plant, but which is not floating. Remember, they are not floating. They are in a tidal the structure which is built by barricading a lake, so they are not coming under the topic that I'm talking. And the ones which is coming under the today's topic is these three: the tidal current, wave, and the other ones, which are much less than 15 megawatt. The wave power, there are many wave power devices. This is the overtopping device where you use a ramp and you let the waves to overtop and then goes into a chamber and then release from that one, and that produce a oscillating column, and that you can produce some electricity. Similarly, you can use waves by constructing a ramp on the seabed and a chamber like this, and produce the vertical movement, and you running a air turbine and get electricity. And this is another famous one. You use a buoy with a submerged base, and as the sea waves are changing, this buoy will go up and down, and that lateral movement is can either convert to a rotary movement, or you can use a lateral generator to produce electricity. So this one is a famous the Palamesis, or I don't know how to pronounce it properly, which is used to produce electricity. So I think I'm in good time. To summarize, the main floating structures that are available for renewable generations are offshore wind with floating foundations, floating PV, and wave power devices. But remember, as I told you, the wind turbines are pretty much the construction wise, they are pretty much similar. For example, if you look at a car, the car has four wheels, the four wheels, the shape is pretty much the same. Similarly, the wind turbines are having three blades, rotating structure with nacelle and so on. The floating PV, again, very fixed structure, modular structure, easy to construct. But you don't find similar wave power devices. Other than the tidal range, all the other wave power devices are different from one to another. That makes their commercial viability less, because you cannot go into mass production and so on. That's probably one reason why you don't find so many wave power commercial projects other than some pilot projects. Because of that, the installed capacity is comparatively very small. But it is anticipated that the offshore wind and the floating PV plants will emerge more and more in the next few decades, and I'm sure we will start seeing few of them in Sri Lanka in the near future. So I hope that you got some message from my nearly one hour lecture, and I'm sure that you do have some questions. So I will pass the mic to the organizers to manage the questions.
Yes, Professor. Thank you very much for the presentation. And now the audience can ask question either as a voice message, or you can use chat option. So you can write your question. Both options are welcome.
Okay, my name is Jeevan Jayasuriya. Thank you very much, Professor Janaka, Ekanayake, for the nice presentation. And I would like to ask you just one question concerning wind power control. Until the wind turbine reach to the rated velocity, there are two controls. I mean, that you were talking about, and the pitch control is done once the rotor has come to the rated velocity, but until the rotor is reaching, while from the cutting to rated velocity, it's still producing. And you showed electronic control. So how it is done? It is just something adjusted into the generator, or is it something not mechanical for sure, because it's electronic?
Yeah.
And I don't
Yeah.
understand what you mean.
Okay, let me answer that question. It's I didn't go into that detail because topic was not in I was mainly talking about the big picture. And now what happens is what you really need is let me pull up a slide very quickly, which will help me to answer your question with just give me a second to. So this is a slide which shows what happened to the generator speed with the wind speed. If you look at the first one, at 5 meters per second, this blue curve. As you change the wind generator speed, the power extracted from the wind will also changes, and you get the maximum at particular point. So if you wanted to get the maximum at 6 meters per second wind speed, you need to change the generator speed. So all we are doing is we manipulate the generator speed, and depending on the type of the wind turbine, like there are, we call it type A, B, C, D. If it is a fixed speed wind turbine, which is the old wind turbines, you are operating on this the vertical line. So you cannot extract the maximum power from the wind. But DFIG, which is the doubly fed induction generator and full power control, can follow this curve up to certain extent. So all you are doing is you change the frequency seen by the generator. By doing that, you can manipulate the kind of synchronized speed if it is a synchronized machine. So that is how you manipulate the generator speed to follow this dark black curve, which is the maximum power extraction curve. I hope that gives you an idea how you do that control.
Yes, thank you. Thank you very much for this answer. Actually, this works for variable speed generators, right? Not for the fixed speed ones.
That's correct.
Yeah. Okay, right.
Yeah,
thank you.
So there are two more questions in chat box.
Yeah, that's. Shall I pick them?
Sure, sir. Please.
Is it possible to have hybrid system like using floating PV along with both? Yes, of course you can do that. I mean, there are the one advantage of using hybrid system is, like you can always use to minimize the variation on one source by the other source. These, the stochastic cancellations, rather than controlling the variation, the stochastic cancellation is a one way of minimizing the variation. So hybrid system is a good option for that. The second question is from Juan Vijayman. Why we can't see any offshore wind project in Sri Lanka long-term plans? Okay, as I told you, the offshore wind is expensive. they have the onshore wind has kind of passed the other conventional plants in terms of cost, but offshore wind has not. They are still expensive. The one reason how the UK and the other European countries justify putting a lot of money for offshore plant is not the cost of electricity production. They are mainly concerned about the energy security. Remember, the UK and some of the European countries get gas from Russia. And if Russia closes their gas pipes, they will not have any of their gas power plant in operation, and they are in big trouble. So they can justify going with offshore wind, even though they are costly, because of that they enhance the energy security. So I'm sure there will be a time the offshore becomes mainstream, and maybe our long-term planning horizon. I mean, remember there are two things. One is the least cost planning, and other one is the policy. If the government says that we must have 80% renewables by 2030, and if it becomes the policy, right now it is there on the manifesto of His Excellency. If it becomes the policy, then we may not have options to obtain that amount of renewables using onshore options. Then we may go for offshore, and even though they may not be the least cost. Second one, before recent SLAAS called for floating solar EOI, there was a project proposed for Madhuroya in 2008. Any reason for fail? I mean, remember, these are politically driven. You are talking about a regime, there is no big power plant added into the system. So I really can't comment on that. There's another question from Danula Balasurya. What are the benefits of floating solar comparing with ground-mounted solar system? I mean, remember, some people are heavily against the ground-mounted solar systems because the places available for ground-mounted solar systems are good lands for agriculture. So you are going to lose so much of agricultural land by putting ground-mounted solar system. On top of that, getting the permission to put up a ground-mounted system is very difficult. Of course, so if you go with the floating solar structure, there will be the protest because you can't disrupt the occupation of the fishermen, so you cannot have impact on flora, fauna, and so on. So there are so many issues. However, if it is a large lake having a the reasonable size floating structure, will not going to create a huge issue. For example, the one I was involved at Mahamaya Lake, we started with fairly large solar farm, but we have to squeeze it quite a lot because there were so many objections from the community, and one advantage is if you go with the bank mounting structure. As I told you, the height of the lake is changing, and if you use the same length mooring structures, then your floating structure either will come closer to the anchoring point or go away from the anchoring point. So, depending on the different the month of the year, your lake, the different part of the lake will be covered by your solar panel. That gives an advantage. So that is why we are thinking of floating solar against the ground mounted solar. There's another question from Somatilaka. Is there any environmental impact from underwater species? Is there any? Of course, there. As I told you, there are. That is will be one of the key studies required before you put up a floating solar plant. As I told you, the one which we did it in Bangladesh involved quite a big team. It was a ADB team. So these are time taken project. You need to involve large consultants to really work out the feasibility. There is a question from probably a foreigner, Kauza Sajib. Is it feasible to use wind turbine or other offshore structure to generate electricity? Because there are a lot of problems like high initial investment, marine life hazard because of noise or bird strikes, disruption of recreation, boating, surfing in offshore area, maintenance cost, noise in those plant area, need of big area, transmission lost, variable loading, and so on. At the end of the day, is it really feasible to use these technologies? I mean, if they cannot be used, you won't see gigawatts of offshore wind farms coming out. Now, remember, one advantage of wind is the foundation is a very small structure, so they are not really interfering with the underneath sea life. Having said that, the wind farms are always an issue for birds, whether they are onshore or offshore. But people, they are trying to minimize these by various ways and putting up these plants all over the world. So I'm sure if they are not feasible, people will not do this. And having so many gigawatt of installed capacity will definitely show that these are feasible options. So you cannot just neglect them. So basically, those are the questions. I find them in the chat box.
Yeah, it seems questions are over. Now I would like to invite Dr. Iresha Attanayake to deliver the vote of thank for the day.
Hello.
Yeah, we can hear you, Dr. Iresha.
Okay. So if there are no any other questions, I would like to thank Professor Janaka Ekanayake on behalf of EUSL Energy Project and the Department of Mechanical Engineering, the Open University of Sri Lanka, and Sri Lanka Association for the Advancement of Science, SLAAS Section C. I would like to thank very informative and very useful, timely presentation. So when I circulate the flyer in the SLAAS also, most of the people, they have commented this is going to be a very timely presentation. Thank you very much, sir. So hope you will join us for some more presentations in future. Thank you very much.
Thank you, Richard. Thank you, Ruchira.
Thank you, Professor.
Thank you, sir. Good night.